Welcome. So, we were discussing about this uh, field in an induction motor, where is Bs, where is Br and where is B net. So, I told you that you have energized these stator coils with a 3-phase supply with appropriate sequence. So, that let us assume it moves in the anticlockwise direction, because I can always make it rotate in the anticlockwise and clockwise direction by playing with the phase sequence of the supply. So, let us assume it is moving in this direction B net, and this will be the net field is suppose there, which is sum of Bs plus Br, and these dots indicates the at that instant when B net is suppose occupies this position, the conductors seeing this B net will have maximum induced voltage, because BLV is the voltage, and the polarity I found out by applying right hand rule, but in an intelligent way. Here stator conductors is not moving, therefore, it can be I have explained that. So, this is dot and this is dot at that instant the induced voltage, although you must appreciate this point. This is quite a complicated windings, 3 phase R, Y, B, all conductors are there, but no matter which conductors come here, they are bound to have maximum induced voltage BLV, that is the crucial thing to understand. So, this is this. Now, the question is, suppose I ask you, this is the maximum induced voltage. Now, suppose take the case of rotor winding, this rotor coil. I want to now sketch the rotor field. Suppose I want to, where is the rotor field, I want to know. Now, you must appreciate one point. Rotor winding, you are shorting it, is not? Rotor winding, you are shorting. Suppose these are the rotor windings and you have shorted it. What do you think? This is a lagging power factor? Yes, it is, because the current induced voltage because of net field, and that has produced current in the rotor circuit IR, IY, IB, and these currents will lag this induced voltage by some phase angle. Therefore, although the induced EMF is maximum for this conductor, but current in this conductor is not maximum. Maximum value of the current will occur after some time, depending upon the power factor angle of the rotor R and X, and it is the current which decides BR, not the polarity of the induced voltage. That is very interesting. Therefore, although these are the dots indicating EMFs, these dots indicate EMFs, peak value of EMF occurred there, no doubt, but the current is not going to be maximum here. And if you look at it, okay, it is at this instant here, rotor is moving. After some time, this conductor will leave this place and come over here, is not? And perhaps at that time it will attain the maximum current. It is obvious, because after some time delay, the current will attain maximum value. Therefore, I can say with confidence that this is the maximum induced voltage here. Perhaps this conductor saw this event slightly earlier, this fellow is now having maximum current, because it has already crossed and come here. So, although maximum voltage is in this conductor, maximum current is carried by a conductor which has already seen maximum voltage, and then its current has picked up, because it is lagging power factor. Therefore, maximum current perhaps will be here in this case. This is dot and it is diametrically opposite whoever is there. It is two pole configuration, you better do. This will be the maximum current. Once again repeating, this conductor is seeing maximum voltage induced, but not the maximum current, because after all it is a lagging power factor load on the rotor side. Load means it is shorted, so its internal impedance R and X. Therefore, the current this conductor will have maximum value after certain time, but after certain time this fellow has moved to this position, because rotor is moving in this direction with a speed n r. So, some time has elapsed, it has suppose come here. Therefore, right now when this conductor is having maximum induced voltage, some one of the conductors on the left hand side will have maximum current, because he has already seen the maximum voltage. Now, its current has become maximum. Let us assume this conductor is dot, whether this or this, it depends upon exact power factor angle of the internal impedance of the rotor coils. That is there, but that is lagging, I know. So, let us suppose this is dot, this is crot, and this is current direction, rotor current maximum dot cross. Now, I told you one thing while discussing rotating magnetic field. Rotating magnetic field, some field is moving, just you understand that this is B net rotating, it is like doing like this. But about one interesting thing is, where the position of this rotating field at a given time, it is difficult to say at every instance, but at some positions I can say very clearly where the rotating field is right now at. What is that? Whichever phase carries maximum current, rotating, suppose at this instant I find R phase is carrying maximum current, the rotating field, resultant rotating field must be along the R phase axis. If Y phase is carrying maximum current, then rotating field will be along the Y phase axis. So, these are the inputs I am already having. Now, here is a situation where I conclude out of so many conductors, they may belong to R phase, Y phase, V phase, I do not care. But I am certain about one thing, that these conductors carry maximum current. It may belong to R phase, Y phase. The resulted field of rotor then must be perpendicular to this line, is not that resultant rotor field must be here. This is the most interesting part. Although it may look like a very stupendous task, I don't know what to do, but I can easily make it out. When B net is here, I am sure B r will be on its right. By what amount, of course, that is to be found out, because I have to then find out what is the exact power factor angle, then I can locate these conductors which are having maximum current now. So, what is the thing? B net right now it is here. I have identified the conductors which will carry maximum current right at that instant when B net is vertical, and I conclude this conductor is carrying maximum current, and then by using the fact that whichever coil is carrying maximum current, BR will be perpendicular to that coil axis or along the coil axis is a perpendicular line there, and then I get BR. BR has to be here, and if BR is there, then I will say, oh, BR plus BS is B net. Therefore, your BS must be there. This is very interesting. So, I can now just starting, because B net is going is BR plus BS, for which the induced voltage will be there. What is the point of calculating induced voltages separately for BR, BS, this, that? I start from that assumption, okay, B net is suppose here at that time, then I conclude these conductors on stator and rotor, they must have peak EMFs with this dot by applying right hand rule correctly, and then dot. Then I argued that okay, this conductor is having maximum voltage, does not mean it is carrying maximum current. Why? Because rotor you have shorted, induced voltage is there, current in the rotor circuit must be the induced voltage by the impedance of the rotor circuit, which is inductive Rx. And therefore, if this is the maximum voltage, instantaneous maximum voltage, at that time maximum current will not come onto the conductor after certain time lag, lagging current. And so, this particular conductor will have maximum current when this conductor is also moving. So, if you allow some time to elapse, this conductor must have moved to the left, and at that time it will have the maximum current. But suppose I am asking you, okay, this conductor is having maximum voltages, not maximum current. Can you tell me which conductors then is having maximum current? Then I will argue, okay, perhaps a conductor like this will have maximum current, because it has already seen the maximum induced EMF when it was here. Rotor is after all moving this way. Therefore, this coil is carrying maximum voltage, induced voltage, but this fellow perhaps will carry maximum current, and once I know that, then I know that whichever coil is carrying instantaneous maximum current, the direction of the resultant field because of that rotor current must be along the axis of that coil, which is this. And once you fix this up, you have started with B net, then BS must be this, that is all. Understood? So, this and then everything B net, BR, BS all are moving with synchronous speed. So, this angle will be delta constant. So, that is why we discussed the production of the torque by considering DC current at a particular position. Okay. But I am sure that same result I can use and say the electromagnetic torque produced will be K some constant, B net magnitude of that, BR into sin delta, where delta is this torque angle. You can say another interesting thing. For example, this is BS I have got. If I ask you what is BS? BS is the, if I draw it separately, it will be the way I have drawn these two are equal. As suppose BS is here, is not BS is, that is how I got BS. If I ask you, tell me out of so many conductors on the stator slots, which conductor is carrying maximum current? I will say, oh, this is BS, then draw a perpendicular line here, and perhaps and not only that, I will be also able to tell the direction of the current I max. Clear? If your Bs, because of stator current, what is the stator field rotating, all are rotating with synchronous speed, omega electrical speed or ns mechanical speed. So, I can also fix up where these rotor currents will be. Okay. I told you one thing that what is called the direction of the torque of the induction motor. I applied Faraday's law and told you, in fact, I have applied Lenge's law to explain that, that is, rotor cannot but rotate in the same direction as that of the rotating field. If you have rotor was stationary, if you close the rotor circuit at t equal to 0, I told at t equal to 0 plus everything is stationary, but both the fields are moving with synchronous speed, and let time passes, rotor moves with speed nr, then also a steady torque will be produced, because the angle between these two fields Br and Bs, they will be time invariant, and you will get torque. But one can also apply what is known as left hand rule to find out the direction of the torque produced. Okay. By applying left hand rule there. For example, here if you see, this is the conductor which carries maximum current, it is your B net. So, B net will be like this cos theta, it will be still like this. Therefore, you apply left hand rule B, this is I, and you will find it is experience a torque like this. Therefore, this is quite interesting. So, although it may look at the very beginning there is a 3-phase winding with so much complexity, this that, but essentially in space these are all space phasors, flux density. Nowadays, you will be hearing about what is the space vector control of induction motor speed, this that. So, you should have a fair knowledge of how to fix up those positions. So, I hope you have understood this very clearly. Okay. Therefore, this. So, it looks like that Br tries to the direction of the torque is from Br to B net, A cross B sort of Br to B net. This is the torque, and the electromagnetic torque will be in this direction. So, in a motor mode, we have already told you that in a motor mode, if you have a motor, I will now simply show like this, your M will be there and electromagnetic torque will be in the direction of rotation of the rotor Nr. Electromagnetic torque is the driving torque, that is one thing, and opposing mechanical torque, that is called the load torque, that will be there. And also I will just symbolically show that on this that Br, if it is here, after some angle Bs is there and this angle is delta, and everything is rotating in this direction for oh, I am so sorry, this is B net. Thank you. So, Br to B net. Now, let us come to the induced voltage expression. I told you that E 1 RMS value of the induced voltage in the rotor is root 2 pi P n s by 2 relative speed between the field and the conductor stator. This is stator per phase voltage stator root 2 pi f, then phi. This flux per pole with respect to whom should I calculate? With respect to B net, that is this flux per pole should be 4 by P B max net L r, where r is the rotor radius, L is the length of the machine, P is the number of poles. So, this is the flux per pole and I must calculate it with respect to B max net, that is B net, B net is B max net. So, B net corresponding to that I will calculate, and also and into K W 1 winding factor and then 1. Similarly, per phase rotor voltage should be also calculated like this root 2 pi P by 2, and this is n s minus n r, assuming rotor is moving with some speed n s minus n r, and this is same phi, same 4 by P B net L r into K W 2 N 2. Acha, here at this point I will do one just simplification to this term. Acha, we have seen that in induction motor this relative speed which is called slip speed is going to play a crucial role in deciding the performance of the motor, etc. Why? Because the magnitude of the induced voltage in the rotor depends on n s minus n r. Maybe larger voltage is induced depending upon this difference. N r could be very low RPM, then difference will be large, more induced voltage will be there. But if n r is close to n s, very less induced voltage will be there, and induced voltage will decide the current in the circuit, and current we know will decide about the B r, hence the torque. Therefore, it looks like n s slip speed n s minus n r is going to play a crucial role in deciding the performance of the machine straight. I mean, there is no doubt. Performance of the machine means in terms of torque, power, this, that. So, for example, if n r equal to n s, rotor there is no induced voltage, you cannot expect any torque to be developed, this, that, no power, no mechanical power output unless torque is there. Therefore, n s minus n r is going to play a crucial role, of which n r is variable. We will show you that depending upon the mechanical load present on the machine, n r value is decided, but n r can change. As at least I have seen it when I have started the machine, n r was 0, then gradually its speed went up. So, n r changes. but Ns is constant. Ns is 2 F by P, mechanical speed, is constant if F is constant. In earlier days, this supply frequency was constant. I could not do anything. Supply frequency is 50 Hz, that is all. But in present day context, F may also vary, but let us assume still our grid voltage is 50 Hz. So, I will assume okay, I will run the machine from constant frequency supply 50 Hz, then this is constant, I can assume. So, speed of the rotating fields are constant and NR may change, and I told you Ns minus Nr is going to play a crucial role, because that will decide what will be the magnitude of the voltage. Not only that, that will also decide what will be the frequency of the voltage, because frequency of the voltage in the rotor circuit or current is Ns minus Nr into P by 2, 2 by P or P by 2. So, frequency of rotor current, of rotor voltage and rotor current. Okay. So, these two things must be understood. This can be assumed to be constant. Frequency of the rotor current depends upon rotor speed, and also the induced voltage in the rotor depends on rotor speed, and rotor speed may change. Anyway, we will continue with this in the next class, but we are going now to a detailed discussion on the induction motor after this, after we have understood where is Bs, Bnet, Br, clarifying the things. Thank you.